Okay, so where were we? So I claimed I wanted to tell you about 3 models. This was a recap of the XY model that we talked about, the S2 version of it. This is the villain model on which I will focus on in this last lecture. So the simulations, the nice pictures I've shown you, you would basically see exactly the same thing with the villain model. Why that? Because if beta is very large, this interaction between nearest neighbor spins is extremely close to this. If you try to approximate E beta cosine theta, you Taylor expand cosine and you will exactly see this, except the Fourier modes 1, 2, 3, minus 1, minus 2, and so on. So this function at very large beta is extremely close to this one up to a multiplicative constant which does not play a role in the Gibbs measure. And therefore, the simulations will locally look exactly the same. You could couple the two systems locally so that they're just the same. But why did we move to the villain model? We moved there because the Fourier coefficient of these 2 pi periodic interaction happen to be much easier to play with than the Bessel type Fourier coefficient of the E exponential of beta cosine. So, as I illustrated in this picture, which said there is no symmetry breaking for the S1 valued, because of this Mermin-Wagner difficulty, we move to the dual model. We will Fourier transform the S1 valued model to its Z dual, and there we will hope to detect a phase transition, a localization, delocalization, which the proof will need to show that this symmetry breaking in Z is relevant for the power law versus exponential decay of the S1 value. So my goal in this last lecture, I have no idea where we will go. Not good at predicting the timing. But at least I know we will succeed in rewriting the partition function of the villain model in terms of a Z-valued Gaussian free field. This we will achieve. Maybe we will achieve to rewrite the 2-point function of the villain model. How does the theta x angle correlate with the theta y angle in terms of a ratio of partition function for the Z-valued Gaussian free field? This, we should manage to do that. Ideally, I'll be able to tell you how we use this Z-valued Gaussian free field to actually detect the BKT phase transition. This would be better for my course, but if not, we can discuss over some dinner. And so that's the plan. So maybe I will not write down the third model I wanted to do, because this was just to highlight a different point. I will maybe read very quickly. Third model. There are many other S1 valued models you may look for, and one of those, and I will do it for S1 and for S2. One of those would be to view S1 as a target manifold and to use an interaction which would be the geodesic distance between theta I and a neighboring angle theta j. So the XY model is this L2 distance squared, but it's as natural, I guess, to have a model which would take the arc distance between theta I and theta j. This will also be a ferromagnetic system which will be S1 valued, as those two models are. And the model will be P lambda beta, maybe a geodesic, I don't have a good name, which will be proportional to the product over I and j of exponential beta length, arc length between theta I and theta j. And as a, sorry, minus beta in this case. As beta goes to infinity, you really want theta I to be very close to theta j. Maybe you want length squared. This would be a more natural analog of the manifold valued spin system. And in S2, you could do the same. You could say this spin sigma I, you want to interact with the spin sigma j according to the geodesic distance between the two. So this is a perfectly legitimate model. One was the Euclidean distance. The second one is the ith kernel between theta I and theta j. And the third model is the geodesic distance between the two. So these are three very natural models. And what can be proved here, if we go back to the first lecture, one can show long-range order in dimension d equals 3 or higher for this and this. And as far as I know, the proof doesn't work for neither of these two. Those are not easily seen to be reflection positive. So the proof by a Fröhlich-Simon-Spencer collapses. The proof in the case of the S1 valued model that we did with Tom Spencer still works, but requires this disorder that I didn't spend too much on. So this would still prove a symmetry breaking with some Nishimori disorder. But with this model, we cannot remove the disorder because G-nib is less clear for this model than for the previous two. And now for BKT, BKT transition is proved when D is equal to 2 on the Z2 lattice. This is proved for this model. This model, I will try to tell you how one proves BKT for this one. And as far as I know, for this one, the proof breaks. So this is just to highlight that if you modify a little bit the way angles interact together, the current proofs of BKT, they're still a bit sensitive to what you are doing. They still need some properties of how the Fourier transform looks, despite that this one is very natural as well. So this third model is there to tell you that the whole theory is sort of robust to the way the lattice looks and all that, but it's not so robust in terms of how the interaction looks.
So you said for large beta, XY, and Villain model, they're basically the same. You can couple them up to the scalar.
Yes, I did say something of this kind, but you could only couple those in a finite window which depends on beta. The coupling will cease to be true at very large distances, and BKT is about a phenomenon at arbitrarily large distances, so this coupling proof will never work. So there is no proof which says we detect BKT for villain, and therefore we have BKT for XY.
But I'm wondering if there is a coupling between the third model and...
Yes, so if there was a coupling, this would be a possible way of proving things, but for the same reason, the coupling will only be local. So, yeah. So, with Paul Dario and Diederik van Engelenburg, we will rather shortly write a paper where we extend a little bit the interactions for which we can have BKT, but this will not include this one. So since this one is just there to tell you that the understanding of BKT is still far from being complete, I will remove it. And now the first thing I want to do is to use this Fourier transform on one edge. I want to use it on top of all the edges of my graph to rewrite the partition function. So the idea in the picture is to take this lambda box, this finite box lambda of Z2. So this is my finite box inside Z2. And along each edge which carry the interaction, I want to use the fact that the Fourier dual of S1 is Z. And I want to use it everywhere. And as a first step, I will rewrite the partition function of the villain model, of this second model on this top blackboard, in terms of a dual model, which we will see will be the Z-valued GFF. So, goal 1, rewrite the partition function. I will recall what this is, Z villain on this finite box lambda in Z2, but the rewriting will not care about the dimension. This will be important later. I want to rewrite it in terms of Z integer value GFF, which I will define in a second. It will live on lambda at inverse temperature 1 over beta. So this will be important, as I emphasize later. And the second thing which will be important, the dual model not only will inverse the temperature, but it will also live on the dual graph. So in fact, I take it back, dimension 2 is nice at this moment, otherwise this would be an issue. So let me start by recalling what is the partition function. This plays an important role when we say that dp lambda beta villain of theta. For most of the course, I told you this is proportional to without being too specific. But if we want to be precise, against the uniform measure on all the points of the lattice, this Radon-Nikodym derivative is given by product I next to j f villain theta I minus theta j. And the partition function is there to make this measure a probability measure of mass 1. So I need to divide by z villain lambda beta, which is defined as we did in the first lecture as an integral z villain lambda beta is an integral on top of all the angle in lambda d theta I of product I next to j lambda of f villain. Maybe I will write down what f villain is, which is sum over m in z exponential minus beta over 2 theta I minus theta j plus 2 pi m squared. So the partition function is just integral over the uniform measure on my angle of how large my Gibbs weight, my modified villain Gibbs weight is. Okay, so I guess below this line is a dangerous line, I assume. Yes, so then let me switch. I will try to write as high as possible. Let me be brave. Maybe I will keep the Fourier transform on the right. This will be useful. Okay, so let's keep computing this, partition function. And what I will do, along each edge, I will just write the Fourier series of these 2 pi periodic interaction. And we will see what pops out of this. So this is the integral, multiple integral over all these uniform measures. But now for each such edge, I will, maybe I will do it slowly. So I have f villain of theta I minus theta j. This is a periodic function of theta I minus theta j. So I will rewrite this as a sum over Fourier mode of f villain Fourier coefficients k e to the I k theta I minus theta j. Now, I introduced the villain model precisely because this Y coefficient is easy to write down. And not only easy, it's Gaussian, so it has, the cross product are very easy to work with. It has many convenient features. So let me rewrite this as integral over those uniform measure of product I next to j, sum over k, e minus 1 over 2 beta k squared, e to the I k theta I minus theta j. So, as I emphasized before, we already see one of the two main aspects, which is the inversion of temperature, which is here. That's important. We don't yet see the dual graph, but at least we see the one over beta. And very often, when we do statistical physics, high temperature expansions, things like that, it's very convenient to inverse a sum and a product. So if you've done some Ising model, you've done this over and over again. And when you do this, a product of sum is a sum of products. But at the moment you exchange, you need to keep track what was the value of the integer k along each of those edges. So let me do it here. This is now a sum of product, and the sum I can exchange it with the integral. Everything is compact, finite. There is no issue of Fubini or anything here. So I have a sum, and now I have integers affected along each edge. And there is a slight subtlety here that I don't want to spend too much time about. What I will do is on my graph, in this sum, for each edge, I will arbitrarily choose an orientation. There are probably better ways to write this down, but each edge, I choose one orientation, because this product is along non-oriented edges. I choose an orientation, and on top of this oriented edge, I choose one integer kij. So those are in a z to the power of the edges, but maybe I have chosen, it's not all oriented edges, I've chosen one direction. And what do I have here? I still have my integral, product of d theta I, and then product over all the edges in my graph lambda of E. So this is now I choose one direct edges, 1 over 2 beta kij squared e to the I kij theta I minus theta j. So the next step will be that I will rewrite this product over edges, not as a product over edges, but as a product over vertices. I will change the perspective. I will try to see what is going on top of each vertex I in my graph. Yes?
The Kij and the index set. What is the index set?
The index set is the directed edges of my graph, and I only keep one representative for each edge.
And that's what the half is for?
Yes.
Ah, okay.
Yes.
And a bit confused about Ij there, Kij. And
So it's
I is also another index, right?
It's I is going to j.
Ah, okay. And this product is then a different I then.
And this product is also I is going to j in
Okay, yes, the P theta, right?
yes. So here I will ask you to believe me. It's not impossible that I will do two mistakes in a row, but they will solve each other. So there is one little subtlety here that this interaction here, this is an odd function. So at this moment, this is not an unoriented edges. It's like in Ising model, it's sigma I times sigma j. There is no orientation. There is no orientation here. But at the moment I do the Fourier transform, it's still an odd function. There is no problem. But when I start changing the sum and the product, I end up with even functions. So I have to be a little bit careful in principle. There are several ways to be careful. The proper viewpoint is to manipulate one forms, but I didn't quite introduce those. Another viewpoint is to break a bit this symmetry, and then everything goes back nicely. But worst case, I do two mistakes, and we end up with the right object. So now that I have this, I want to rewrite things from the viewpoint of the vertices. So I'm still summing over those integers affected to those oriented edges. If you don't like those, one could say that I am summing over one forms of my graph that are z-valued. And the one forms have the property that kij is equal to minus kji, and that's the right viewpoint. So
Kij is in Z to that.
Yes, thank you. That's it. This. And if you don't like, you could say that K lives in the, okay, one needs a notation, one forms z-valued one forms on lambda. So that's Kij along one edge is minus Kji. So I am summing over this structure here, and I am integrating product over I in lambda. Now I can erase my recollection of the Fourier coefficient. D theta I, and product over I in lambda, and I will try to see what do I come up with on top of each vertex I. And I claim that I will have e to the I, theta I, and now sum over j next to I, k ij. And here, if ij was a directed edge in my graph, this is the kij. If it was not, I use this recipe to say that kji is minus kij. Okay, so for example, this one comes with kij times minus theta j, which is minus kji times theta j. So that's a much better writing. Why? Because this is an integral over the uniform measure here, and it's a product which involves only theta I. So I can decouple the integral by saying this is a sum over those one form kij.
What happened with the square?
Oh no, this is something terrible happened. I forgot about the square. So thank you for this key question. So there is still the square. I can put it here because it doesn't involve theta. So I can put it here a product over I and j, e minus 1 over 2 beta chi ij square. And I don't count edges twice here. So thank you, otherwise I will have a terrible problem along the road. So I rewrite this with this term, e minus 1 over 2 beta chi ij squared. So this starts looking a lot like a GFF weight, except it's not an integral over r to the power lambda, but it's the sum over those one forms. And then what do I have here? I will invert the product and the integral. I have a product over I in lambda, integral from 0 to 2 pi, d theta of what? Of ei theta, some j next to I. So I'm sorry, this I and this I are not the same. Sorry about that. K I j.
Looks like a divergence.
It is a divergence. Exactly. So now, if we look at this in the eyes, so I'm just slightly unhappy about one thing. I want to claim that this is this integral is zero. No, is zero. No, I'm happy actually. So this is zero if this sum, which is a divergence, is non-zero. If divergence of k at I is non-zero, because if I have, for example, k equals this term which I call the divergence, so by definition this is the divergence of the one form k at the point I. If this is 1 and you integrate e to the I theta on 0 to pi, this will give 0. So the only chance for this integral to be non-zero is that the divergence of k at that point is 0. And this integral will be 2 pi if divergence of this one form at the vertex I is equal to 0. Are you okay with this? So in other words, in this big sum, each one form which at a single point, at any point in my graph, has a non-zero divergence, will kill this term here. So I can finish the computation by saying that this whole partition function, there is this term here which will not play any role. This is 2 pi to the power the number of vertices in my graph times sum over kij, those one forms which are such that the divergence of this one form is 0 at each point of my graph. So it's a divergence-free one form on my graph. I will make one example of those. So I have sum over those, and what is the weight that I have? I have product over I and j, I next to j, of e minus 1 over 2 beta chi of ij squared. So unless there are questions, I will write on a very small piece of lattice what is a divergence-free one form, and how can we interpret this in a nicer way. Yes?
Does it go like, just not for traditional functions, but if I want the correlation, I can write as the ratio of two.
Yes, so this I will go back to this after. So at this stage, I only wrote what the partition function is, but we want to understand how things correlate with each other, so I will have to also write down what the two-point function is, and this will be the same business. The only difference is that I will allow 2 points to have a non-divergence. So I will insert a divergence at one point and remove it somewhere else. But first, the partition function. So let's write on a very small lattice what would be one such. I have one piece of a lattice here, so that's good. I'm very lucky with the sequence of blackboards today. Okay, so I will try to make one not too difficult to visualize, otherwise. Okay, so let's imagine that I've chosen this direction here and I have 1. So maybe here I can have 2, but if I have 2 here, I have 1 floating here, 2 out. I need maybe 1 here, and maybe 0 here. If I have 0 here, maybe I can put 1 here, 1 here, and maybe 0 like that. Let me make my life quite simple. Maybe I can put 1 like this, and then I need to put 1 like that. Maybe 0 here, 0. Let's try maybe something dangerous, that I have 1 here. I'm forced to have 1 here. 1, 2, I would need 3, but let me make 5. Then I need 2 here. Okay, this is getting 0, I need 1. I need 6. If I have 6, I need 6 here. I hope I won't. I might have a problem at the end.
Das ist Thouless on the
But
right.
this one,
Yeah, this one is not good.
And the right hand edge, that 1 is coming, but nothing is, I think, is going to be.
Where? Here?
No,
All right.
Here?
One down.
Yes.
Oh, yes. Okay, let's simplify things a bit. 0, 5, 5, 3, and then 2, 2, 1. Good. Okay, so that's one form which will contribute to the partition function of what? Of the villain model which lives on those vertices. Okay, and how will it contribute? It will contribute with the product along these edges of those integers squared, exponential those integers squared, times 1 over 2 beta. The hope is that if beta is very large, if this spin field is very correlated, the dual one, which will appear in a second, will not care so much. We'll be able to put a lot of integers, will be fluctuating a lot. That's what we want to see, and we want to extract information from that. So playing with one forms is not so easy, but if the graph is planar, we will be able to play with an easier model, which will be again a 0 form or a 2 form. They are dual to each other by Poincaré. And I want to try to tell you what this proper dual model is. So here I will put a Dirichlet boundary condition outside. Here I'm going a little bit too fast, but my villain model was a free boundary villain model. The angles can do whatever they want, including on the boundary, like a free boundary Ising. My dual model, if I have free, will be at the opposite of the spectrum, will be a Dirichlet boundary. And then how do I make a function out of it? It's a little bit like the height function of the Dimmer model. When I cross one of those edges, I change the height of the function accordingly. So here I will have 0, here I will have 0, 0, and here I will have 1. So I need some convention here. Here I have 1, here I will have 2, which is consistent with this, and so on and so forth. So I will have 1 here, I will have 3 here. I don't want to continue, I'm sure things will happen well. Where does the constraint that the divergence is 0 come in? Let me take this vertex. The divergence is 0 because if I sum all the exiting arrows, I will have 0. What is the interpretation of this sum of 4 integers? It's just the gradient 1 minus 2 plus 1 minus 1 plus 3 minus 1 plus 2 minus 3, which needs to be 0 if you have a well-defined function here. So all this to say out of this small experiment that out of a divergent-free one form on the planar graph, you can produce a height function which assigns one integer to each placket of your graph. Okay? So with this example, I claim that I can rewrite this sum over divergent-free one forms. It's exactly the same as 2 pi to the lambda, but this will not play any role in the fluctuation of this dual object. Sum over n of f, where f is now the faces or the two cells or whatever you want of my planar graph lambda. Sometimes this would also be written the dual graph of the planar graph lambda. So I'm summing over, so those leaves in z to the power the faces of lambda, which is also the dual graph of lambda. Each face here carries an integer, and the face outside carries 0, which I don't write here. So I'm summing over those things. And now what is the Gibbs weight? The Gibbs weight is very nice because it will be a product over a face F next to a face G. So I was doing the product over those edges. It's the same as the product of those orthogonal interaction of E minus 1 over 2 beta n of F minus n of G squared. And now this looks exactly like a Gaussian free field. The only difference is that I don't have an integral, I have a sum. And my fibers, they don't live in R to the power all the places where they have a value, but they are in C. So this is the partition function. This is the partition function of it's called an integer valued Gaussian free field, which is the same thing as a GFF, which is conditioned on a zero probability event that the GFF belongs to Z. So it's a GFF with an inverse temperature, which is not beta, but 1 over beta. So we rewrote the partition function of the villain in terms of the partition function of the different models, which maybe I can show the slide again that we had earlier. Can I show the slide, please? So I now justify that the partition function of this villain model, whatever the temperature is given by the partition function of something which to each placket of my graph assigns an integer. And it's an easy exercise to show that this model has symmetry breaking if this beta is low and so this 1 over beta is large, if this is a low temperature. This is the much harder part. And just to see it written here, the definition of an integer valued GFF is a probability measure. I call those n. In this slide it's called psi, but it's the same model. So I'm sampling a psi collection of integers on my graph according to the same Gibbs weight as a GFF, but those psi are z-valued. So I've stolen two pictures here. One by Hélène, which is a beautiful picture of this measure when you relax the constraint that psi lives in Z. So here it would be var phi lives in R. It's the GFF on an n by n grid. I don't know what n is. N is large. And if you ask for this field, if you condition this Gaussian field to be Z valued, you are no longer Gaussian and you look like something like that. I didn't find a typical picture, but I found a large deviation such picture in Lubetsky-Martinelli slide. I think this is the solid and solid one, but okay. They look like some things like this, which are more discretized version of the GFF. And so, in what follows, I want to tell you how the two-point function can be written down in terms of this z-valued height function. And I will have to be brief in why can we prove BKT out of those. So that was a very short slide, but with a picture. And now I will write the two-point function. So
actually, this calculation holds in any dimension. You just get a integer value Gaussian two form in any dimension.
that's correct. But yeah, in any dimension, you can do the same computation. But to resolve this divergence k equals 0, you can write it using a two form on the plaquettes of the d-dimensional graph. But it will not be quite GFF on the D cells of the graph. But yes, something of this vein survives in dimension larger. And in fact, you can use this viewpoint to prove long-range order for villain in Z3, for example. Okay, so I think I could have saved some of those information for the two-point function. I will do it from scratch in a more sketchy way. So let's write the two-point function. So we want to understand what is cosine of theta x minus theta y in a big domain of Z2 at inverse temperature beta for the villain model. So what we should think of is we have a very big piece of Z2. We take one point x here, one point y here, and we want to understand how the angle at x correlates with the angle at y. So this is the same as e to the I theta x minus theta y. That's a tiny observation, but it's sort of important. Why? Because by symmetry, the theta field has the same law as minus the theta field. So I can rewrite my two-point function in this way here. Once I have done that, this is an integral against the uniform measure of the Gibbs weight that we had before, F villain theta I minus theta j. But I insert two things. I insert e to the theta x and e to the minus I theta y. So this is almost the same computation as before. I have the partition function in the denominator. This one is what I computed for you before. But on the numerator, I have exactly the same type of structure, except I have those 2 points that I have here. So imagine I run exactly the same argument as before. On the numerator, I will have sum over all these one forms here ij. I will have the term I forgot, and thanks to Antoine, I can put it again. E minus 1 over 2 beta kij squared. And then I have a product over all the points in my graph, integral d theta I, or d theta, e to the I theta times sum for all the let me call it theta I, for all j next to I of chi ij. So far, it's exactly the partition function. The only difference is that if I is equal to x, I have one further integer. And if I is equal to y, I have minus an integer. So let me say that this is plus a Dirac point mass at x and minus a Dirac point mass at y. Right? And in the denominator, I have exactly the same thing that we had before, and I don't have delta x minus delta y. This is the partition function that I had before. Here is a small trick which is very useful when you are, like me, often confused with orientation. You can always think of this modulo plus or minus 1. Why? Because this would also be correct with a minus that you have here. So you don't need to be too careful with whether you have plus or minus. You have to be careful with the fact that the sign of this is minus the sign of that. This one is important. So once we have this, if I keep doing what I did before, I will have sum over 1 from k, which are such that the divergence of k at I is 0 everywhere except at x and y. And in fact, in what I did before, it would be minus delta x minus delta y. But since I only think of it modulo plus minus 1, I don't need to be too careful. So this is already convenient here. I mean, what that means is that I need to choose one of the two. I'm not summing over the two altogether. So I'm summing over all the one forms that are perfect dual of ith function, except there is a tiny problem at x and a tiny problem at y. And then I have product I next to j of e minus 1 over 2 beta chi ij squared divided by kj. The divergence is 0 everywhere. Product I next to j, e minus 1 over 2 beta chi ij squared. So the 2-point function is the ratio of two partition functions. One is the partition function of an integer value GFF. The second one is not quite an integer value GFF. There is this little nastiness at x and at y. But the whole point of the proof is to say that if beta is very large, if the temperature of the villain is very low, those are not very costly, and it's not too difficult to insert this defect into the very fluctuating z-valued field. And if it's not very difficult, this is why this ratio will be polynomially decaying instead of exponentially decaying. So to give you a slight flavor of how things are working, I will do one proof for you, which doesn't prove BKT, but I think does give the flavor of it. I will try to analyze what is the 2-point function of the villain model when both x and y are on the boundary of my planar domain. On the boundary, this will be easier to rewrite things. If x and y are in the middle, there is a monodromy issue to be solved. But I will just tell you what is going on when we are on the boundary. So let's imagine that I have a big two-dimensional box, and I want to detect a change of behavior between x and y at the boundary. So let's take a huge 2D box. And let's make x here and y here. let's imagine you have a one form which is divergent free everywhere, but here it has divergence 1, and here it has divergence -1. So it's as if you pump some liquid with a strength 1 at x, and you remove this liquid at strength 1 at y. How can you interpret this such a one form? I claim that it will be the same as a GFF that we had before, but with Dobroshin boundary condition. If you have one boundary condition everywhere here, and 0 here, then if you look at the one form which is induced by the gradient field, you will have divergence free at all the vertex inside by the same argument as before. But at this vertex you will have divergence 1, and at this one you will have divergence -1. So in other words, if I do the computation above, the 2-point correlation function between theta x and theta y when x and y are on the boundary is exactly a ratio of partition functions which are very easy to visualize. If x and y were in the middle, you see that we wouldn't be able to do exactly this. But here it would be the partition function of the integer value GFF. Here. With Dobroshin 0,1 boundary condition divided by the partition function of the integer value GFF with 0,0 boundary condition. And now comes the main reason behind BKT. If beta is very small, it means 1 over beta, which is the inverse temperature of this dual model, is very large. And if you have a z-valued height function in this domain, you will see an interface between the positive part of your field and the negative part of the field. And this interface will cost something like exponential minus 1 over beta times the length, at least. So this is a huge cost, and you can make a Peierls argument to show that this will be less than exponential, a constant which depends on beta, times x minus 1. So if beta is small, by this dual argument, I can make a proof to you that there is exponential decay of correlation. It's the worst possible proof of exponential decay, but it goes through the dual model, and it's a perfectly rigorous proof if you do in all the details. The idea is now that if beta becomes large, 1 over beta becomes small. So now maybe your Gaussian free field is less sensitive to the fact it's conditioned to be in the integers, it moves more. And if you believe that this field delocalizes, becomes square root of log n big, maybe those Dobroshin boundary conditions are less of a problem for your field. And those new proofs of BKT, they take Pete Lammer's argument so that this delocalizes, and they manage to massage this in a very non-trivial way to say that this ratio of partition function, they are not so small, they are polynomially small. Thanks to this delocalization of this surface, which is less sensitive to the presence of those forced falaise cliffs. So, do I have 5 minutes? So, in the last 5 minutes, I don't want to tell you what one does when the points are in the middle. It induces, it's called an order-disorder operator. It's a very nice story, but I have 5 minutes. I just want to very shortly give you a last bit of story in this, without any technical detail. So I will go to the slides for the last 5 minutes.
Does the divisional energy of this Dobroshin bound, if you have a harmonic extension of this Dobroshin boundary condition, does the divisional energy of that play a role in the is that sort of?
I didn't hear very well, but let me reinterpret maybe. The Dirichlet energy of the best possible, of the harmonic extension of this is something which is polynomially small, which is good. So if if the z constraint was not so important, you would explain the polynomial decay.
Yeah.
But you are z-valued, so...
No, yeah, that's what I just integrated that so you can predict the polynomial decay using the harmonic.
Yes, exactly. That's a good question. You cannot use this in any way to prove, but this is intuition. So a first point I want to make is that playing with the Coulomb gas, since next week there will be, I think, talks by Ofer Zaitouni, Oren Widor, Marek Biskup, probably about maximum of Gaussian fields. You may ask yourself, if you constrain your field to be z-valued, what's going on for the maximum of those new fluctuating fields? And with Avelio, we definitively couldn't get the log-log-n fluctuations and any concentration or anything. But since I had a couple of questions on this yesterday, we could prove that the maximum of the z-valued field is always strictly below, macroscopically below what you would have if you have the R-valued one. So it really affects, in a quantitative way, how smaller the maximum is, and this comes from the contribution of the vortices. And a second bit of information, okay, so this transfers to upper bound, which involves vortices for the two-point function. So this was the question of AO, I think, that there is a 1 over beta GFF, this is there. And this is the additional input that the vortices create. And Fröhlich-Spencer, which is a more conceptual, even lower bound, tells you that BKT holds at a low temperature at large beta. So in the last 2 minutes that I want to tell you is that if you now move to this more mysterious part of the story, which is the S2 valued model, which is believed to kill the BKT phase, I can tell you about 2 results. The first one is a result with Yuan Aru and Avelio Sepulveda. What we did is that we revisited a series of papers by Patrasiu-Zeiler, and in those papers, so they had only 0.5% of the physics community with them, 99.5% with Polyakov, but still, their series of papers was saying, if Polyakov is correct, then it must be the case that if you sample S2 valued spin system and you project it down to an XY model, so you condition your system on the vertical direction and you look at the remaining randomness, that's easy to see that this is exactly an XY model, but in a random disorder, where the closer you are to the north or the south pole, the smallest the beta is along those edges. And Patrascu and Zeiler were saying that if you project this system, in order to kill BKT, you would need to have a lot of those islands with a high temperature, with a small beta. And they didn't believe that you have sufficiently many such islands to create a mass. And with Yuan and Avelio, we were able to show that indeed, those islands, in a certain strong sense, they are very small, they don't percolate. So for a while, we thought maybe the 0.5% towards Patrascu-Zeiler was a bit too small. And so we didn't know which scenario would hold, either very tiny islands, and in that case in favor of polynomial decay, or maybe non-percolating areas of high local temperature, which would be in favor of Polyakov. We proved that this scenario in some sense holds for Polyakov, and nevertheless, we could exhibit an example of such a scenario with several axioms for which a mass exists. So we didn't prove Polyakov in any possible mean, but we rigorously disproved the line of argument of Patrascu and Zeiler. So we built a random field of conductances for the XY model, which does have a mass. And the very last slide is that a year and a half ago with Paul Dario, we tried to look at the other side of this story, namely what happens if you analyze XY model on a percolation cluster. So the induced disorder in Polyakov is not an ID percolation cluster, but with the mass you could say that this is something very uncorrelated, a bit like a percolation cluster. And there we could say that BKT survives all the way to the edge critical point of Z2 percolation. And to do this, we couldn't go through neither of the proofs that I've shown, so we had to find a detour to say that BKT is stable to this disorder. And I had 5 minutes, I did 7, so I should stop right now. Thank you.